Welcome back, everyone. So in this video, we're going to talk about rewriting logarithmic expressions. So you may have seen this before in Algebra 2, but we're still going to go through it step by step as if you've never seen it before. So in this case, we're going to be both condensing and expanding these logarithms. So these properties down here should hopefully be kind of a recap. So in condensed form, if we're looking at product property, the values in the argument will be multiplied. But if we want to expand it, we're going to give each value in the argument its own logarithm, and we're going to be adding them together. And then kind of the same idea, if we have any division happening in a single logarithm, we're going to expand it, or condense it, vice versa, by giving them each their own logarithm, and we're going to subtract them. And then with power property over here, if we have an argument value that's being raised to some exponent, what can happen is, in order to quote-unquote expand it, we're actually going to take that exponent and it's going to become a coefficient. So that n value is just going to be written in the very front. So starting off, we're going to condense each of these logarithms. So in order to condense them, what you also need to pay attention to is the bases. The bases must be the same. So when I'm adding two of these logarithms with the same base together, I can take the arguments and I'm going to multiply them. So this would just be the same as log base 4 of xy. Then number 2, I'm subtracting, and my logarithms have the same base, so because I'm subtracting, I'm going to condense by dividing them. So this is going to be log base 3 of 5 over z. And then looking over here, so with number 3, what I like to do when we have a lot of terms, or anytime we have 3 or more terms, I like to look at the signs of each of those terms, and that kind of tells me whether it's going to go in the top or whether it's going to go in the bottom. So if I look at my first term, we have just log of x. There's no sign in the front, so that means it's positive. Anytime a value is positive in a logarithm and we want to condense, we're going to write that value in the top. And then if your value is ever negative, that means we're going to write that argument value, we're going to write it in the bottom. So it's also negative over here, which means this will also be rewritten in the bottom. So when I rewrite my log, so this is going to be log of my x value, which is on top, and then I have 5 and z on the bottom, so that would be log of x over 5z. Now look number 4. So I have a coefficient, and then with coefficients, what happens is these are going to become exponents. So I'm going to rewrite this as log base 2 of x cubed minus log base 2 of y. And then because I'm subtracting these values, I'm going to rewrite them as division. So in a single log, I'd have log base 2 of x cubed over y. Then number 5 here. So my coefficients, once again, these are going to become exponents. So I'm going to rewrite this as log base 7 of a squared minus log base 7 of b raised to the 5th plus log base 7 of 4. And then, of course, I have a positive, which means the first term is being in the top. Second term is negative, which means I'm going to write the argument in the bottom. And then the last term is positive, so I'm going to write that 4 in the top. So this is going to be equal to log base 7 of 4a squared over b to the 5th. Okay, and then this one right here, this one's going to be a little bit more tricky, and that's because we don't have the same base of a logarithm over here. So what I need to happen is I need to include a value over here that has a log base 6. So I'm going to rewrite this as 2 times 1, which I know, hear me out, it's going to sound insane, plus log base 6 of x. Now, what I need to happen is I need to rewrite the 1 as a logarithm with base 6. So that's going to be 2 times log base 6 of 6, and then plus log base 6 of x. And then, now that I have a coefficient of that logarithm, that's going to be rewritten as an exponent. So this is going to be rewritten as log base 6 of 6 squared plus log base 6 of x. And of course, I am adding these two values together, so I'm going to multiply them in a single log. So this would be log base 6 of 6 squared, which is 36. And then my x value over here, which would just be included. So log base 6 of 36x. So now we're going to expand the following logarithms. So with these, so if they're being multiplied together in a single argument like this, we're going to add each of those individual terms together. So this would just turn into log of x plus log of y plus log of z. Then over here, so same idea, each of these base values, or argument values rather, is going to get their own logarithm. So this will be log base 2 of a plus log base 2 of b raised to the 5th. And then what I want to do is my exponents are going to become coefficients. So I'm going to rewrite this as log base 2 of a plus 5 times log base 2 of b. Then number 9 here. So I have 3 values that I need to rewrite. I have the 8, the x, and the y. So when I look at my 8 and my x, both of these are in the top, so I'm going to add those values together. And then my y value, since it's in the denominator of this logarithm, I'm going to subtract that value. So this would be equal to log of 8 plus log of x, then minus log of y. So now over here, now we're looking at a natural logarithm. So the log properties are still the same. It's just a type of logarithm that we're working with, but it's all the same. So what's going to happen is I'm going to have natural log of 7, which that's going to be positive since it's in the top. And then both the 10 and the x are in the bottom, so I'm going to subtract both of those. So minus natural log of 10 minus natural log of x. Okay, and then number 11. So once again, I'm going to separate all these argument values together, or separate them. So log base 7 of 12 plus log base 7 of x raised to the 5th plus log base 7 of y squared. And then all those exponents are going to become coefficients. So I'm going to have log base 7 of 12 plus 5 times log base 7 of x plus 2 times log base 7 of y. Ta-da! Okay, yeah, let's go ahead and do 12. So with number 12 here, so we have the natural log of the square root of x minus 1 over x plus 1. Now, what so many people seem to forget is if I have the square root of something, let's just say the square root of x, that is the same as raising it to a 1/2 power. So what I want to do is I want to rewrite this as natural log x minus 1 over x plus 1, all raised to the 1/2 power. So there's multiple ways that you can actually approach this problem. Personally, I like to do it this way. So I'm going to quote-unquote distribute that exponent to the numerator and the denominator. That is an exponent. It's going to be kind of hard to write that. Close enough. All right, and then what's going to happen is because those are being divided, I'm going to subtract them. So I have natural log of x minus 1 raised to the 1/2 minus natural log of x plus 1 raised to the 1/2. And then you're going to do your power property, and then you're going to move those exponents to coefficients. So this would be 1/2 natural log x minus 1 minus 1/2 natural log x plus 1. So that would be your simplified version. Or rather, your expanded version. Okay, and then we have log base 3 of ab squared all cubed. So what I like to do with this one is I like to distribute the exponent when possible. So this is going to turn into log base 3 of a cubed and then b to the 6th. So then with the exponent properties, that was power property. Now my logarithm properties, I'm going to do product rule. So I'm going to expand. So log base 3 of a cubed plus log base 3 of b raised to the 6th. And then I'm going to do power property. I'm going to move those exponents to the front, making coefficients. So 3 log base 3 of a plus 6 log base 3 of b. All right, and then 14 and 15 are just longer versions of them. I do want to go ahead and do 14 because there is a couple parts in here that are actually pretty important. So with this one, so I'm going to start off with labeling what goes in the top and the bottom. So 64 is in the top, so it's going to be addition. X to the 5th is in the top, so it's going to be addition. And then the 16 is going to be subtracted. Y to the 7th subtracted, and z is going to be subtracted. So when I rewrite, so I'm going to have log base 4 of 64 plus log base 4 of x raised to the 5th minus log base 4 of 16 minus log base 4 of y raised to the 7th minus log base 4 of z. Now what's important here is whenever you can, you want to rewrite your logarithmic values as constants when possible. So you want to ask yourself, log base 4 of 64. This is the same as asking yourself 4 to what power gives you 64? Well, in this case, that's going to be 3. So this would be the same as rewriting it as 3 plus log base 4 of x raised to the 5th. And then over here we have log base 4 of 16. So 4 raised to what power is going to give you 16? Well, that's going to be 2. So then I'm going to write minus 2, then minus log base 4 of y to the 7th minus log base 4 of z. So now we're going to combine like terms and then do power property. So 3 minus 2, which is just going to give me 1, and then I'm going to do power property with all these. So 1 plus 5 log base 4 of x minus 7 log base 4 of y, and then minus log base 4 of z. So that would be your simplified form. Well, expanded form. All right, now we're going to move on. So this is all just kind of the same. It's just tomato, tomato. I'm going to skip all these. So we're going to go down to inverse properties. So this is just a very fancy way of doing what I call circle of life. So if I were to have a logarithm here, and I want to do the inverse property, so if I do circle of life, that's going to be b raised to the x equals the argument. Well, that would just be b raised to the x equals the argument, which is b to the x. And then what happens is the logarithm was eliminated. So we're going to do the same idea if it's in exponential form. So this is in exponential form, we want to rewrite it as a logarithm. So I would have log base b of an argument value of x, and that's going to equal log base b of x. So that would be log base b of x equals the exponent, which is log base b of x. So once again, when you get here, your logs would simplify, and we're just left with the arguments. So that's essentially what we want to happen, or what we want to happen. So over here, what has to happen is your base of your exponent and your log, they have to be the same. So what I'm going to do is I want to solve for an unknown value. Now, because some of these are going to have a variable in them, I don't want to set it equal to x. I'm going to set it equal to another letter. So I like to just use the letter n. That's just me. So I'm going to convert from exponential to logarithmic form. So this is going to be 2 raised to the n is equal to log base 2 of 5. So 2 raised to the n is equal... Nope, I need to go to logarithmic form. My bad. So this is going to be log base 2 of n equals log base 2 of 5. And now that we have the same log base, I'm going to set the arguments equal to each other, which means my unknown value here in this case is going to be 5. So your quote-unquote unknown value, it could be a constant or it could even be an expression. So that's why I don't like to use x, because I don't want you to think of it like an equation. We're just rewriting it. Okay, now in this case, I have 7 raised to the log base 7 of x minus 5. So I'm going to set that equal to my unknown value of n. We are in exponential form, so I need to convert it to logarithmic form. So that's how I meant to start the previous problem. So log base 7 of n is going to be equal to log base 7 of x minus 5. So this would be log base 7 of n equals log base 7 of x minus 5. Now, once again, we have the same log base, so when those cross out, we're just going to look at the arguments. So that means my mystery value is just x minus 5. Okay, I'm going to skip over to number 29. So with a natural log, your base is not written here, but when it's a natural log, you know, hopefully, that we're looking at a base of e. So I'm going to set that equal to my unknown value. So I'm in logarithmic form, so I'm going to convert it to exponential form. So I'm going to do e raised to the n equals my argument here. So e raised to the n is going to equal e raised to the 5y. So now that we have the same base in exponential form, I'm going to set those exponents equal. So my mystery value is 5y. So what a lot of people ask me when I get to this part is, what the heck am I doing? Like, what is the point of this? So the idea is we're rewriting and we're kind of getting rid of the fluff, essentially. It's like when you're writing an essay and you have like 10 paragraphs and you get it down to 5. We're doing the same idea here. We're just getting rid of the excess. We're getting rid of the fluff. And we're getting rid of the fluff by using inverse properties. So instead of writing 2 raised to the log base 2 of 5, I can just write it as 5. Like, all this is unnecessary. Same idea over here. 7 raised to the log base 7 of x minus 5. The 7 and log base here are unnecessary. It's the same as just writing x minus 5. So like I said, we're just getting rid of the fluff. Okay, so let's look at 30. So I'm in exponential form here, so that means I want to rewrite it in logarithmic form. So once again, I'm going to set this equal to some unknown value n, and then do circle of life. So we have e, or log base e of n is equal to natural log of 12. So if I rewrite it as log base e of n equals natural log of 12, well, a log with a base of e is a natural log. So I'm going to rewrite this as ln of n equals natural log of 12. And now that we have a logarithm with the same base, I'm setting the arguments equal. So this is the same as just writing 12. So we got rid of the e in the natural log. It's the same as just writing 12. Okay, now with 31, these are the problems that I really wanted to get to. So with these types of problems, remember the actual exponential base and the log base have to be the same in order for those to actually simplify and eliminate. But this 8 can be rewritten with the base of 2. So I'm going to rewrite this as 2 raised to the 3rd power times log base 2 of 3. Now what's going to happen, in order for me to be able to convert, whoops, should have wrote my n value. So in order for this to convert, I need to get rid of this 3 right here. And what I'm going to do is power property. I'm going to make it an exponent. So I'm going to rewrite this as n equals 2 raised to the log base 2 of 3 cubed. So unfortunately, we do have an exponent within an exponent, which is tragic. But I'm going to rewrite this. So this is equal to some mystery value, which is 2 raised to the log base 2 of 3 cubed, which is 27. So now I'm in exponential form, so I want to do circle of life and convert it to logarithmic form. So when I do that, I'm going to have log base 2 of n equals the exponent. So log base 2 of n is equal to log base 2 of 27. Now my log bases are the same, so I can set those arguments equal. So this is the same as just writing 27. All right, and then looking at 32. So now we have 14 raised to the log base 2 of 2. Well, if your log base and the argument are the same, this is essentially asking 2 to what power gives me 2? Well, that's just an x value of 1. So what happens is anytime you have a log base and the argument has the same value, that's just going to simplify to 1. So we have 14 to the first power, which is just 14. So we didn't even have to do circle of life on that one, which is nice. Okie dokie. I'm just going to keep doing these because I know people need a lot of practice with these. All right, so we have e raised to the third power times natural log of 5. So I'm actually going to start by doing power property. So I'm going to turn that 3 into an exponent. So this is going to be, some unknown value is equal to e raised to the natural log of 5 cubed. Now this is the same as writing n equals e raised to the natural log of 125. So now that I have that logarithm simplified, I want to rewrite by doing circle of life. So I'm in exponential form, so I want to go to logarithmic form. So base e of n goes to natural log of 125. So this would be log base e of n equals natural log of 125. Now remember, if I have a logarithm with a base of e, that's the same as just doing a natural log. So I'm writing that in parentheses just to kind of give myself a little bit of distinction and separation. So now that I have the same logarithm, set my arguments equal. So my mystery value here is the same as just writing 125. All right, 34. So with this one, same idea as before. I need the exponential base and the log base to be the same. So I can rewrite 36 with a base of 6. So my mystery value is 6 squared, then times log base 6 of 4. I'm going to move the coefficient of the exponent to the exponent of my argument. So this is going to be n equals 6 raised to the log base 6 of 4 squared. So this is the same as 6 raised to the log base 6 of 16. So I'm in exponential form, so I'm going to do circle of life to convert. So I'm going to have log base 6 of n equals log base 6 of 16, which means this is the same as just writing 16. Okay, so let's go ahead and skip over to 36. So it's the same idea, but now we're going to throw in a variable. So I need the exponential base and the log base to be the same. So I'm going to have n equals 2 raised to the third power times log base 2 of 7x. Once again, I'm going to do power property. So n is equal to 2 raised to the log base 2. And I'm going to raise the entire argument to the third power. So I do need to put parentheses around the argument in this case. So when I rewrite, you can either evaluate or you can go ahead and rewrite in a different form. It's really up to you. I'll go ahead and rewrite first. So I'm in exponential form, so I want to go to logarithmic form. So log base 2 of n is equal to the exponent. So log base 2 of n is equal log base 2 of 7x all cubed. And then, of course, set the exponents, or not exponents, set the arguments equal. So n is equal to 7x all cubed. So either that could be your answer, or who knows, we may make you simplify it. So 7 cubed, which is going to be 343 x cubed. So either one of those could be expected. And then I just go nuts. So this is just me losing my mind. So once again, unknown value. So n is equal to 125 raised to the log base 5 of 2x all cubed. So I'm going to rewrite 125 with a base of 5. So 5 cubed times log base 5 of 2x cubed. Now, if you're anyone like me, you don't like having an exponent of an exponent. So I'm going to go ahead and rewrite 2x all cubed. I'm going to rewrite it as 8x cubed. Just to go ahead and just get rid of it. That way it's one less thing I have to worry about. So now I'm going to do power property, move it to the exponent. So my unknown value is going to be equal to 5 raised to log base 5 of 8x cubed. Nope. All cubed. Cubed again. And then, nope. Now I'm ready to rewrite. So I'm in exponential form, so I want a log form. So log base 5 of n is equal to that exponent. So this is going to be log base 5 of n is equal to log base 5 of 8x cubed, all cubed. So I'm going to set those arguments equal since we have the same base. So this is n equals 8x cubed, all cubed. So mathematically that would equal 512, x raised to the third. Nope, 9th. So that's the same thing as what we have. Gross. Okay, now we're going to do change of base. So the change of base here is going to be really similar to what we did in exponential form when we were looking at horizontal shifts and looking to see how that would look like as a vertical dilation. It's the same idea, but now we're going to actually involve change of base. So you have your change of base formula over here. So your base that we want is what you're going to write here where your a value is. So like let's just say I've got log base 4 of, 3. Let's say I'm going to rewrite it with a base of 2. So if I rewrite it with a base of 2, I would have log base 2 of 3, which is the argument, over log base 2 of the original base. And then you could simplify it from there if possible. So like log base 2 of 4 actually simplifies, so this would be log base 2 of 3 over log base 2 of 4, well, that's just 2. And then that could even be rewritten as 1/2 times log base 2 of 3. So the idea here is we're looking at the original, and you're going to be writing whatever the new base is. So looking at 38, so the function f of x is equal to log of 6x is a horizontal dilation of the function g of x, which is log of x. So you want to show that f can be rewritten as a vertical translation of g, where f of x is equal to g of x plus k, where k is a constant. So what I like to do with these is I like to write out all the information first, because every time I read these problems, I feel like I have to do like a mental double take. So f of x is log of 6x, whereas g of x, in this case, they're telling me is just log of x. So I want to rewrite f of x as a vertical translation using g of x. So I want to take f of x over here. So I know f of x is equal to log of 6x. Now I'm going to use my log properties and I want to expand f of x. So this is f of x equals log of 6 plus log of x. Now what they also did tell me is that g of x is equal to log of x. So right here, I want to replace log of x with g of x, since that's what we're really wanting. So this is f of x equals log of 6 plus g of x. So when I look at the actual answer that we want it written as f of x equals g of x plus k. So I have f of x equals something plus g of x. So that mystery value here, this is what we want. So that tells me that my k value is log of 6. That would be my vertical translation. So we didn't actually do any change of base yet, but we're about to. So with 39, so we're going to let f of x equals log base 4 of x and g of x equals log base 9 of x. We want to show that f is a vertical dilation of g by finding the value of k such that f of x equals k times g of x. So once again, I have a mental double take that I always do when I do these. So I'm going to start off with just f of x and g of x. So f of x is log base 4 of x And then g of x is log base 9 of x. So what I want, my general setup, we're looking at f of x is going to be equal to some value of k times g of x. So when I sub in my values, I know f of x is log base 4 of x, and that's going to be equal to k times g of x, which is log base 9 of x. So what I want to do is I need to change the base. Now, what people ask me is, how do I know which one to change? Well, I want to get k by itself, so I want to get rid of log base 9 of x. So what that tells me is, because I want to get rid of the log base 9 of x, I need to make the left side have the same base as the right side. So I need to change log base 4 of x to log base 9 of x. So that tells me over here the left side is going to have to do a change of base. So I'm going to do log base 9 over log base 9. So I'm going to take the argument, and that's going to be the argument in the numerator, and then I want the old base to be the argument in the denominator. And then that's going to be equal to k times log base 9 of x. So I'm going to rewrite this. So I've got log base 9 of x over log base 9 of 4. And that's going to be equal to k times log base 9 of x. Now remember, what we're ultimately solving for is this k value. So I need to get rid of that log base 9 of x. So you can either divide both sides by log base 9 of x, or my personal preference, let's move it over, I'm going to multiply both sides by 1 over log base 9 of x, which is the same thing as just dividing both sides, but to me this just looks a little bit more clean and organized. Okay, so I'm going to create a new row just so you can kind of see what's happening. Okay, so on the right side, so the log base 9 of x is going to simplify with the log base 9 of x, and then on the left side, log base 9 of x divided by log base 9 of x. So what's left is we're just going to have k equals 1 over log base 9 of 4. So this is 1 equals, nope, k is equal to 1 over log base 9 of 4. That would be your k value. That would be your vertical dilation value. So with that, I would implore you to do 40 and 41 on your own. Okay, so with this one, it's going to be, or with 40 rather, it's going to be the same idea, but now we're going to switch it up a bit. We're going to flip them. So now f of x is going to be equal to log base 9 of x, and then g of x is log base 4 of x. So once again, I want to rewrite this as f of x equals k times g of x. So when I sub in my values, so we're going to have log base 9 of x equals k times log base 4 of x. Now remember, I want to get k by itself, which means I want to get rid of log base 4 of x. In order to get rid of it, I need the left side to match the base on the right side. So when I go through a change of base, I'm going to rewrite, so log base 4 of x over log base 4 of 9. And then that's going to equal k times log base 4 of x. So I'm going to multiply both sides by 1 over log base 4 of 9. So when I do that, so log base 4 of 9, nope, not 9, sorry, x. It's like, hold on, something's not right. There we go. Sorry, y'all. So log base 4 of x, log base 4 of x, log base 4 of x, log base 4 of x. Those are all going to cross out. So we're left with a k value of 1 over log base 4 of 9. There we go. Sorry about that, y'all. Okay, 41, last but not least. So now we're going to have, same idea, we're still writing it as a vertical dilation. So f of x is going to be log base 4 of x, but now g of x is going to be natural log of x. So we decide to throw a natural log in there. So once again, we're still going to have f of x equals k times g of x. So when I sub in, so log of 4, or log base 4 of x is equal to k times natural log of x. So remember, I want to get rid of natural log of x, so I need the left side to match the same base, or to have the same base. So that means I need a logarithm with a base of e, since we're dealing with a natural log. So I want log base e of x over log base e of 4 equals k times natural log of x. Now, if I have a log base e, that's the same as writing a natural log. So this is the same as natural log of x over natural log of 4 equals k times natural log of x. So when I multiply both sides by 1 over natural log of x, so natural log x on the right side simplify, natural log x on the left side simplify. So I'm left with a k value of 1 over natural log of 4. That would be my vertical dilation. Ta-da!